Hello everyone, and welcome to my lecture on the photoelectric effect and how the process of photosynthesis uses the properties of electrons to produce energy. By the end of this lecture, you will understand how photons excite the electrons in chlorophyll B molecules, know how this excited state is passed between chlorophyll molecules, understand how electrons in water are ionized and transferred to chlorophyll A, and understand the modern implications of these topics. Just for a bit of review on this topic, as many of you already know, the photoelectric effect is a phenomenon discovered by Albert Einstein in 1905, and it describes the ability of electromagnetic waves, such as photons, to eject an electron from a material. This equation is hopefully one you recognize by now. Energy equals Planck's constant times velocity, and it is used to determine the velocity of an electron ejected from a material. Electrons are not always ejected from the atom, however, as you can see in the bottom diagram. A photon is in the midst of striking an electron on the first energy level of this atom. However, the photon does not contain enough energy to completely remove the electron from the atom. In this case, the electron absorbs the energy from the photon and uses it to ascend to the next energy level. This is what is known as an excited state electron, and it will be vital in our understanding of photosynthesis later on in the lecture. Chlorophyll is a pigment which absorbs energy from photons to use in photosynthesis. Those of you taking biology will know that a pigment is a molecule which absorbs only certain wavelengths and reflects others. Inside of a plant cell there exist many chlorophyll molecules, each of which can absorb this light energy. This absorption of light is a result of the photoelectric effect, and the photons absorbed by this process will be stored in excited electrons. Once the electron returns to its ground state, it will release a photon as well as a bit of heat. This is vital to the energy transfer in photosynthesis, and we will come back to this in the next slide. This diagram shows the photosystem involved in a light-dependent reaction. In order to progress the reaction, the photon energy received by the initial chlorophyll B molecule, shown in yellow here at the top, must be transferred to the chlorophyll A molecule in the center of the photosystem, shown in green here at the bottom. So how does this happen? Well, as mentioned previously, when an electron returns to its grounded state, it releases energy in the form of light and a tiny bit of heat. As shown in the diagram, chlorophyll molecules are closely packed together, and this allows them to easily transfer energy from one molecule to another. Since electrons release photons when they return to their grounded state, these electrons can be absorbed by the electrons of neighboring chlorophyll molecules, and using this method, the photon energy can hop between the many chlorophyll B molecules and reach the center chlorophyll A molecule. It is important to note, however, that for every transfer that the chlorophyll molecules make, a tiny bit of energy is being lost due to heat. Thus, the center chlorophyll A molecule will obtain less energy than what is initially possessed by the initial chlorophyll B molecule. After all the energy from the photons of light collected by the pigments have been stored up in chlorophyll A, electrons are required in order to take the energy to the next phase of photosynthesis. These electrons come from a water molecule, which breaks down to generate two atoms of hydrogen. There is a small problem, however. Once the hydrogen reaches the chlorophyll A molecule, how are we going to separate the electron from the atom? Well, this is where the first part of the photoelectric effect comes into play in photosynthesis. With all the energy collected by the photosystem, chlorophyll A can release its light energy into the hydrogen electrons, which excites them to the point that they reach their ionization energy and leave the atom. This creates two excited electrons which can be used to power the processes which produce energy for the cell. It is also important to note that not all wavelengths of photons will be absorbed by the pigments in the plant. For simplicity's sake, we've stuck to only using chlorophyll when referring to the various pigments in plants. However, there are many more pigment molecules that we will not cover in this lecture. Similarly to atoms, each pigment molecule inside of a plant has different absorption spectra, and they all contribute to the overall absorption spectrum of plants, shown on the top right graph. Unlike atoms like iron on the bottom right graph, however, plant pigments have evolved to strategically absorb some frequencies more than others. In plant cells, chlorophyll has proven to be a poor converter of solar energy, and too much energy can overload and kill the chloroplasts in a plant. Because most of the sun's rays are within the green region of the wavelength spectrum, approximately 483 to 520 nanometers, the chlorophyll contains substances which reflect this kind of light, and substances which limit other harmful light sources so that it does not damage the chloroplast. Using the concepts described in this video, attempt the question above. This isn't vital to learn for your understanding of this topic. However, it will help cement the information presented in this lecture so that you can better understand the topic. Suppose the excitation of a pigment electron produces a charge of 3.5 electron volts. However, 0.20 electron volts of energy is lost per transfer of the light energy due to heat. Using the figure below for reference, how many cycles would it take to produce enough energy to ionize the electrons of two hydrogen atoms if the ionization energy of hydrogen is 13.6 electron volts? Now, take a minute and attempt to solve this problem. You don't need any complex formulas to solve the problem. However, you will need a good grasp of the topics presented previously to solve it. Have you attempted the problem? Okay, let's move on. The first part of this problem is fairly simple. We can clearly see from the diagram that 4 transfers of energy are made between the chlorophyll molecules. So, from the initial chlorophyll B molecule here, we have 1, 2, 3, and 4 transfers of the energy. By multiplying the amount of electron volts lost per transfer by the amount of transfers made, and subtracting that from the initial voltage of the chlorophyll B molecule here, we get 2.7 electron volts, or the amount of energy transferred to chlorophyll A molecules per cycle of the system. The next step we're going to take to solve this problem is to determine the total energy required for this reaction to occur. We can see that for one hydrogen atom, it would require 13.6 electron volts of energy, but a water molecule has 2 hydrogen atoms. Thus, we're going to have to multiply the total ionization energy by 2 to get the total of 27.2 electron volts for the amount of energy we need to separate 2 electrons from the hydrogen molecules of water. Finally, we can figure out how many cycles is needed for this reaction to occur by dividing the total voltage needed to remove the electrons, shown up here, by the total energy donated to chlorophyll A per cycle on the bottom here. This gives us a total of approximately 10.074 cycles, or, using our knowledge of significant figures, it would end up being approximately 10 cycles for the total process to complete. Obviously, this is a very simplistic look at the process, and we didn't account for other variables such as the transfer of energy from chlorophyll A to hydrogen. But hopefully this exercise helped to cement your understanding of the overall processes involved in light-dependent reactions. You may be wondering, why does this matter, or why should I care? While this may not affect us all that much, discovery in the absorption spectra of plants and improved efficiency of the photosystems in plants have revolutionized modern botany and pharmaceuticals. Looking back on the question from the previous slide, an increase in the rate of excitation in pigment cell electrons could result in higher photosynthetic rates, and thus higher growth rates as a result of increased rates of photosynthesis. By intensifying the wavelengths of light absorbed by plants, and minimizing the light reflected, the growth rate of plants can be optimized. This has been effective in increasing the production rates of pharmaceuticals and vegetation, but with the legalization of marijuana, it has become even more clear how necessary these systems are. According to Stat Canada, since marijuana was legalized, rates of usage in 18 to 25-year-olds has increased from 17.5 to 27.6%, and has increased in people 26 or older by 26%. With the increase in demand for marijuana, many companies changed their production methods from a typical light-based method to a more effective artificial light-based method. In conclusion, to give a brief overview of all of the learning objectives posed in the beginning of this lecture, photons excite the electrons in chlorophyll by colliding with them and being absorbed to elevate the electrons to the next energy level. The excited electrons in chlorophyll molecules release photons when they return to a grounded state, thus passing the energy to another chlorophyll molecule. The electrons in the hydrogen atoms of water molecules are ionized by the photon energy collected in chlorophyll A. And finally, the atomic spectra of plant pigments are used to determine the optimal wavelength pattern to maximize the efficiency of photosynthesis in plants. Thank you all for watching, and I hope you enjoyed my lecture on photosynthesis and light-dependent reactions and how the chemical and physical properties of electrons affect these processes. I hope you learned something new in this lecture and had fun doing it. Have a great winter break.